Hello everyone and welcome back to the channel. I am Mohan Das, PhD in Industrial Computer Science and Artificial Intelligence. Today in our diffusion model series, we'll finally explore the stable diffusion, the text conditioned latent diffusion model. If you're not familiar with concepts like diffusion model or latent diffusion model, do not worry. I've already covered those topics in previous videos of the series. You can find the full playlist link in the description below. So what are we going to cover today? Nowadays, many text to image models on the internet where you provide a text prompt and the system generates a corresponding image. Most of them are based on stable diffusion. It is one of the most popular and widely used models in this category. Here are a few examples of images generated using Stable Diffusion. They are generated using the latest version of Stable Diffusion, but we are going to stick to the initial version of Stable Diffusion for now. So what makes this Stable Diffusion different? As we saw in the last video, it is the latent diffusion part and the text conditioning. In the previous videos, we have discussed how to condition on class label time steps. However, in Stable Diffusion, there is time step conditioning, but along with it, there is text condition. Now comes the question, how does this text conditioning work? Let us look at the architecture then. We start with an autoencoder. The image is encoded into a latent space, here Z. Once the diffusion process is completed, this is the forward diffusion, this is the reverse diffusion, the latent space representation is again decoded back to image space. This makes the computation highly efficient because now the diffusion process happens at a very small, tiny, and compact resolution. Now, to guide this generation process, we introduce text conditioning here. For example, let's say if we want to generate an image of a cat, we pass it to the diffusion model and it generates something like this. But how the model understands? This is done using something called as a CLIP, clip model, a model trained to associate images and their corresponding caption. For every caption in the dataset, clip encodes the text into an embedding and the corresponding image into an image embedding. And then the model learns to align both representation, something like this. So here all the corner pairs should have the highest alignment. In Stable Diffusion, we only use this text encoder part. For instance, let's say if we want to caption a cat, it goes through the text encoder and it generates a text embedding, which is then used in the UNet. So this is the basic architecture of the clip model. You pass in your text and you get corresponding embeddings here. These embeddings are then used for cross attention throughout the UNet layers. This text embeddings are then used by the UNet model through cross attention layer. Here you see cross attention, and through different downscaling layer as well, downscaling and upscaling layer. This is how the UNet model understands what text it needs to follow. Now we import a few libraries and then we import all the models that we want to import, all the components of the model. So in this component, we need the VAE. So this VAE will help us do the latent diffusion. It will compress from image resolution to a latent space. Then UNet will do the diffusion step. This tokenizer and text encoder are for text conditioning. Then the scheduler, which will decide how much noise to add and how to denoise. We can quickly test the model by using Stable Diffusion Pipeline function from the Diffusers library. We load the VAE, text encoder, tokenizer, UNet, scheduler, everything into this pipeline. And a very simple thing we have to provide is the prompt. So after we initialize the pipeline, we pass in the prompt and we say how many number of inference step it should use. We move the pipeline to the GPU. And now we execute this to see the output. Yeah, so we get a very nice picture of a cat. But now I don't want you to stop here because our goal is to understand what goes inside the Stable Diffusion pipeline, how it is generating this image from the text itself. So now we are going to deconstruct that. So first, once we have the prompt, next part is tokenization. We tokenize the prompt using this tokenizer. Even if the prompt has only 2 tokens, the sequence is padded to 77 tokens because it is a model parameter. And if we plot it, you see the size is 1 cross 77. And this is how the tokenized text looks like. You see, these are the 2 tokens representing a cat, and these are all padding token. And this is the start of text token. All right, then we'll pass this thing into the text encoder and we'll get the embedding. And this is what our embedding looks like. Our embedding has 77 sequence dimension, and each token has 768 dimensional vector. And now we'll use this the encoded text as conditioning into the UNet. And I want you to refer to this image, this particular image. So here the ZT here, what we start with the random latent, and this is how we initialize the random latent. It has 1 cross 4 cross 64 cross 64. So 4 is the channel and 64 cross 64 is the height and width. This is the latent dimension. And we'll start with this. So this is the ZT. Then inside the denoising loop, this is what we pass into the UNet model. So we pass, of course, the latent, the timestamp, and the conditioning, the text conditioning, which is the text embed. And inside this UNet function, the cross attention is handled within automatically, and you get how much noise that needs to be removed. And using the reverse diffusion step, we can just do like this to remove the predicted noise from the latent. And now this latent have lesser noise. Another thing what I did is just to see the progression, how does it look while denoising. I decode them back after every fifth interval just to see how the progression looks like. So let's see. All right, so this one does not look like a cat at all. It's not following the text we have given at all. But why is this happening? So for that, we need to understand a new concept called classifier-free guidance. So what happens is if we generate without any guidance, the output might not follow the text prompt accurately. This happens because the model sometimes relies more on the noisy input than the text. So to address this, we use something called classifier-free guidance. According to this, we use two different prompts. One is the prompt that we want the model to follow, and an empty prompt. So this is for unconditional generation and this is for conditional generation. We do the same, the tokenization step, and we get the text embedding. Now we say in the text embedding, we have two different tensors, each representing one caption. Now during the denoising step, the only change is here. We concatenate the latents two times. This noise prediction also has two prediction, one for unconditional, one for conditional. When we deconstruct this noise prediction, we get this is for conditional, this is for unconditional. And this is where we use both of them. Basically, we combine both the conditional and unconditional noise prediction using the guidance scale parameter. Here you see we have a parameter called guidance scale, which I have set to be 7.5. When the scale is greater than 1, the model moves further away from the unconditional prediction and closer to this conditional, resulting in more faithful adherence to the prompt. And now if we run this, we get a proper image of a cat. You can also change the scheduler, because different scheduler have different effect on different models. So you can play around with different scheduler to find out whether they change the output. For my case, they did change the output by just changing the scheduler. It looks something like this. Now we'll use the same stable diffusion model to do image to image diffusion. So first what I did is I just created the vanilla stable diffusion pipeline just to run a first inference, and we get image of a cat. And to use the image to image pipeline, we call a different class of pipeline called stable diffusion image to image pipeline. And in there you can pass all the components like this. And now you have your image to image pipeline ready. And here I have an image of Donald Trump that I manually edited. And when calling this pipeline, you need, of course, a prompt, a image to start with, which is controlled, and this strength represent how much editing you want to do. So if it's 0, then there will be no editing. If it's 1, then there will be maximum amount of editing possible. We have gone in depth about this strength parameter in one of our video of image to image diffusion model, and you can check that out for more info on this particular one. And if we run this, we get some image like this. You see it coherently merged the neon hair with the entire image. And let's say what happens when I do, let's say 0.8. So the more strength I do, that means more noise is added to the actual image, and the original image structure is lost, leading to greater deviation from the original image we started. Let's say if I do 0.2, then there will be minimal changes to the given image. You see, there is very less change. Now we'll talk about inpainting that we have already discussed, but how we use inpainting in the context of stable diffusion. So I have again the same image of Donald Trump, and this is the mask. The white regions you see are I want to inpaint, and the black regions I want to keep. For inpainting pipeline, you can directly call stable diffusion inpaint pipeline dot from pipe, and it will do the job. And during when calling the inpaint pipeline, I am passing in the prompt called black hair Jay-Z, the reference image, the mask, how much change I want to do to the original image, the guidance scale, like how much text adherence I want, how much I want the generation to be faithful to the given prompt, and number of inference steps. Here, every parameter has a role to play. You need to find out the best one for your generation. So now you see, we get a nice hairstyle for Donald Trump. So yeah, that was it about this video. In this video, we explored how stable diffusion extends latent diffusion model with text conditioning, how clip embedding introduces semantic understanding, how classifier-free guidance ensures alignment with the prompt, and how the same framework supports text to image, image to image, and in-painting task. These three form the foundation of most diffusion-based generative models. In the next video, we'll discuss ControlNet, a powerful extension that lets you control the generation process more precisely. Until then, if you're finding this series helpful, please subscribe to the channel. All codes and resources are linked in the description below.